Thank you all for giving up a little piece of your Saturday to spend this time learning about Scala. I appreciate that. I know you should be out there enjoying this wonderful weather here in Hamburg, because I've been told it doesn't happen very often. You can see the sun out there today, which is amazing. Anyway, I'm really happy to be here today, and I'm really grateful that you all were able to come on such short notice. I'm grateful to Felix for helping to put this together, and Liam, thank you for helping to make this happen as well, and everyone else who was involved. I really appreciate that. So I've been programming Scala for quite a while, actually. How many of you are new Scala programmers? Anyone fairly new Scala programmer? A few people? More than a few? Wow. Great, awesome. That's awesome. Always glad to see new faces to the Scala community. Scala is a very powerful programming language, and you can write some really amazing software with it. So welcome to Scala, and I hope you stay for a very long time. I hope you don't leave for Haskell, because there's plenty of good stuff here in Scala. How many of you have been programming for like 5 years or so? Oh, wow, nice. Anyone here been programming for 10 years or more? Okay, oh, nice. All 5 of us. Okay, we're the old school Scala programmers. Yes, we've been programming for a very long time. You program 10 years, and you see a lot of Scala, and not just a lot of Scala, but a lot of different versions of Scala. And eventually you can come to the conclusion, or at least that you get to understand more when people look at Scala and they're like, hey, there's just way too many things, way too many ways to do something. And that's because when you've been writing Scala for 10 years, you see radically different styles. Scala is a very flexible programming language. It allows maybe too much flexibility in how you can solve problems. And that leads to the question, if we're building a large-scale code base, and we've got a bunch of team members now, and we're going to hire even more over time, and if our application is going to last a really long time, so it's going to last many, many, many years, we're building a product, not just doing a consulting project, then the question is, when we have all these choices, what are the best ones to make? What are the ones that are going to help our team members write correct, maintainable code over time? And not just help our current team members, but what are the choices that are going to make it easier for new developers to come on board and ramp up quickly? And as you might suspect, opinions may differ on this. So today I'm going to give you just a few tips that I picked up over the years that help me write Scala code that's easier to understand and easier to maintain, and hopefully easier for new people to take a look at and know what's going on. And in every one of these cases, I'm going to try to explain to you why I think this. So I'll give you a little bit of justification for why I think this might be a better way to write Scala. And then at the end of the day, if you disagree, that's fine too. Like, there's plenty of room for all of us in the Scala community, and nothing should ever trump your ability to get stuff done. And if you find a way of working that is useful to you, then no one can tell you that's the wrong way to build software, because it's working for you. And at the end of the day, that's the most important thing. Let's get started. I will cover 12 tips to writing better Scala. And these will be sort of random sampling of stuff from data. So how do we use Scala to do data modeling, to construct models of business domains and so forth? How do we use Scala's inheritance facilities? Because Scala is an object-oriented programming language, not just a functional programming language, but also OO. How do we use functions in Scala? And finally, what are some tips around Scala's type system? Data. In an object-oriented world, there's a whole domain called object-oriented data modeling. And in object-oriented data modeling, typically what we do is we create either abstract classes or interfaces. For example, in this slide, I created one for abstract event, representing the parent of a typical event hierarchy. And in our application, there'll be many different kinds of events. In OO data modeling, what we would do is we would create different subtypes of abstract event, and different subtypes would contain different type-specific details. And then we would try to describe the commonalities in the abstract class, in the parent class. And it turns out if you model this a type of problem in an object-oriented way, then you run into certain problems. Chief among them, let's say we want to copy an event. So we want to copy an event, which means that we need a function that can copy any event type E that's a subtype of abstract event. And to copy it, we have to match against all the different subtypes. And then we have to, inside there, we have to ascertain the structure, and we have to be able to create a copy of that, in this case with the specified name of the event changed. And because of the way we're modeling it, we need to be able to return the same subtype that we were passed in. So the only way to do that in this particular case is to do an unsafe cast. So I've seen lots of Scala code bases that use techniques like this to model data. And inevitably the result is unsafe casts, lots of type parameters, lots of type parameter bounds. And Scala actually has a much simpler way that you can use to model data. And that involves using so-called algebraic data types. So algebraic data types, a scary name for something that's very simple. Basically, if you model all your data in Scala with either a case class or a sealed trait, and if your case classes extend at most one sealed trait, then you are building a data model that would be considered an algebraic data type. Algebraic data types consist of two things: products, which can be thought of as records. So in this example, I have person here, and person is a record that contains two fields. Products, in general, contain some number of terms, and every term is a field inside of a case class. They're kind of like a table in a relational database. A table contains a value for every column. That's what a product type is. Some types are a bit different. Whereas product types contain all their terms, some types contain exactly one of their terms. An example would be either. So either is a sum type in Scala, and either has two terms, left and right, and every either is either a left or it's a right, but it's not both. Product types and sum types are dual. In this example, you could see I created a contact, and every contact here is either an email or a phone. What makes contact a sum type is the fact that we're sealing that trait, which means that there can exist a fixed number of subtypes of contact, and that's known statically. So we know, and the Scala compiler knows, that every single contact in the world, every contact in our code base, is either an email or a phone, but of course not both, and there are no other possibilities. These two ways of modeling data are sufficiently powerful to model every single thing in your business domain very precisely. Doesn't matter what it is, you can model it with just case classes and sealed traits. You don't need the traditional object-oriented techniques of building interfaces and abstract classes that you extend at multiple points in your hierarchy. And an advantage of doing this is that it makes it very easy to describe commonality as well as difference. We describe commonality with products. If you want to take the preceding example of the abstract event and refactor it over to use ADTs, then we push all the common parts of that data type into ordinary fields in a case class. And then, of course, there's the part that's going to be different for different types of events. We have a purchase event and refund event and so forth. Those are the differences. We encapsulate all of those into a sum type, and we take that sum type and we add it as a field of our product type. So what this allows us to do is create a pure algebraic data type representation of this particular problem, which of course makes it super trivial to do things like changing the name. It becomes ordinary case class copy. Now, algebraic data types are insanely powerful. They're so powerful that you can create a precise data model of almost anything you can imagine. For example, you could create a precise data model for an email address. You could actually create an ADT that will not allow you to represent an email that's invalid. But that's, quite honestly, that would be a huge amount of work. You would spend a lot of time reading through RFCs and designing a bunch of sum types and a bunch of product types, and you would end up with something that's quite beautiful and amazing, but it probably would take you 2 or more weeks to do that. And we don't always have time. So in reality, we tend to cheat as developers. We cheat. We say, okay, well, we need a model of an email, or maybe a model of an account number or a model of something like that. And instead of using a type that precisely describes the shape of our domain, we use something that's bigger. An example would be string. So we can use a string to model an email address precisely because string contains all email addresses. Unfortunately, it contains a lot more than just email addresses. So we can form an empty string here, and we can pass that around in our application to different functions. And then when they get one of these emails, it basically is bad data. It has an illegal state. And whenever our application logic is working on bad data, its behavior is undefined. We don't know exactly what our application is going to do when we pass it bad data. And there's two possibilities, and you've probably seen them both in production actually. One possibility is a function gets bad data and blows up. It throws a runtime exception. And that brings down the server, or at least crashes the connection, and we get the error in the log and so forth. That's the good scenario. So when that happens, that's your golden. That's fine. It's nothing to worry about. It's a pain. And the bad scenario is when your application keeps working in the presence of bad data. Because then the bad data makes it to your database and this REST API over here and all these other places and starts contaminating and infecting different parts. And suddenly you've got a gigantic mess on your hands that just keeps on growing. And it takes a while to figure out what's going on, and also it takes a while to fix that. You've got to back out any changes that were introduced because of the bad data. So in an ideal world, the state of our application logic, would always be well defined. And that requires us to create domain models that can only represent legal states inside our business domain. Which means our goal in using ADTs is to make it impossible to represent illegal states at runtime. Now, like I said before, it's very, very expensive to do that in the general case, especially for complex data types like email. So what do? Well, there's a technique called smart constructors that lets you gain the benefits of an ADT, but without the large amount of cost. No one has 2 weeks to sit down and create an ADT for an email. However, all of us have enough time to create a smart constructor. What smart constructor does is it basically just guards creation of some data type. And it's not going to allow you to create a value of this type unless the data that you're passing it is valid. So this is a pragmatic solution here. This is a compromise. We're saying we're still going to represent an email with a string. However, we are not going to allow you to construct an email unless that string actually represents an email. So it's a lot easier to do validation than it is to do modeling. It's very easy to check if a string can be an email. So in this solution we actually make the natural constructor of this case class private, so no one can call it. And then we introduce our own constructor in the companion object of email called fromString. And this one is going to do some checking. It's going to make sure that that email is valid before it's going to construct an email. Very simple technique, only takes a few lines of code. And there are libraries out there to help you do this, like Refined and Adjective. And these libraries can sort of there's a little bit of boilerplate here. They can take that boilerplate away and help you do it at even lower cost. And if you apply this technique pervasively, both ADTs and smart constructors in your code base, you're going to get your application into a very healthy state where your application logic only ever works on domain objects that have a meaning inside whatever domain you're working on. It only works on valid data, no bad data in your system. And that's a wonderful place to be. It cuts down on runtime errors, and it ensures that bad data can't corrupt external systems, which is the hard part to back out when that happens. In this example, we can't even call send email with an invalid email anymore because we can't get our hands on an email that's invalid. The only way to make one of these things is to use the smart constructor, and the smart constructor is going to refuse to create an email unless the string we pass it is valid. Number 3, embrace variance. So Scala has support for subtyping. And subtyping has an interesting effect on the way you create generic data structures. Java doesn't have this feature called declaration site variance, but Scala does have it, and using this feature called declaration site variance is going to enable you to build custom generic data structures that infer much better. In this example, I've created this little cache value sum type here. Every cache value is either cached or it's uncached. And you can see here I am not using any variance annotations on this. You know that because the type parameter A of cache value has no decoration. It's just sitting there by itself. If I were using Scala's feature for declaration site variance, then it would have either a plus or a minus sign there. But in this case, this is the way most developers will go to create a generic data type. They'll just stick the they'll stick the type parameter there with no annotation. That's the most obvious way. That's how you would do it in Java. That's how you would do it in many other programming languages. But Scala has this wonderful feature called declaration site variance that is absolutely critical to getting the most out of Scala's ability to infer types. In this example, let's say we create a function feed here that takes a cache value of an animal. And then later down the road, we create a cache value containing a dog. Because of the way we declared this generic data structure, we actually cannot feed dog to the feed function. And the reason for that is a cached dog is not considered to be a subtype of a cached animal, even though dog is a subtype of animal. So if we want the subtyping relationship of the element to reflect the subtyping relationship, or rather if we want the subtyping relationship of the cache to reflect the subtyping relationship of the thing inside the cache, then we have to use declaration site variance. And to do that, it's fairly simple. We just add the plus annotation to A, and then Scala will give us a bunch of warnings and stuff. We'll have to fix up some methods to make sure that we do this in a sound way. But basically, you add the plus sign to A, and then now when you go to execute the preceding code, it'll work just fine. Now, the plus sign there means that in all the methods and or fields inside cache value, that A type parameter occurs as an output of the method or field. So it's something that you get from a cache value. The plus A says, I'm only going to get A's out of there. On the other hand, if you have some data type where you feed A's into it, then you would use the minus sign annotation. And that's the difference between plus and minus. Plus says, I'm going to get it out, and minus says, I've got to feed it in. And as an advanced technique, there will be some cases where you have a type parameter and you get it out, but you also have to feed it in. There's an advanced technique that you can use to split that invariant type parameter into two different pieces, the part that you feed in and the part that you take out. And that technique, splitting the invariant parameter in two, into the invariant part or the contravariant part and the covariant part, enables you to maximize Scala's ability to infer types in situations like this and more complicated examples. So I understand this is not enough time to really cover variance. We need more time if I want to teach you declaration site variance and subtyping and all that stuff. But it should be enough time to at least hopefully set a reminder in your brain so that next time you have type inference issues with some generic data type you created, most likely it comes down to not using declaration site variance. And that's the point when you can go Google this and read a tutorial or two or watch a video or something and learn how you add these plus and minus signs to your type parameter positions so that you can make your type inference problems go away with custom data structures. And number 4, the last tip around data is learn to love folds. So folds allow us to take what can be somewhat boilerplate code and minimize it, expressing our intent more concisely. In this case, we're going to load some configuration, and if we got back an error, we're going to return the default configuration. But if it succeeded, then we need to add a bunch of overrides to the configuration as determined by the add overrides function. So this is not terrible, but there's a certain amount of boilerplate here. And the boilerplate comes down to the match keyword and the two different cases, and the fact that we have to bind things inside the left and right. We have to bind variables to them. In this case, we have to bind something to config. And then we have to call functions on the variables that we bound. And this is not terrible. If you like doing this, then this is fine. But it turns out that if you use the fold method on data types like option and either and list and so forth, then you can cut out all that boilerplate. And you can create something that is significantly easier to read once you've gotten used to the style of calling fold. Now it's a big jump from this to this, and it takes some time. You've got to become familiar with fold. But once you become familiar with fold, then suddenly you look at this and you're like, okay, on the left-hand side, we're returning the default. On the right-hand side, we're feeding the value of the loaded config to add overrides function. And this expresses that same intention, but without all the pattern matching boilerplate. And here's another example where a common pattern in Scala codebase is to map over something and then call get or else. And that map or get or else is basically a weird way of encoding a fold on the option data type. You can rewrite any combination of map followed by get or else into a single fold, where the thing that you stuck in get or else you're now passing as the first parameter of the fold, and then the function that processes what was inside the option and does something with it is the second argument to the fold. So that fold function is on a lot of Scala data types, both in Scala's standard library and outside Scala's standard library. And once you get used to one or two folds, you become familiar with that pattern, and you're able to effectively utilize it in your own code base to eliminate the boilerplate of pattern matching and variable name binding. Inheritance. So Scala supports subtyping and class extension, inheritance, all this stuff that came from Java and other object-oriented programming languages. And there's a few tips I want to give you around inheritance that will help make your code bases a lot cleaner and a lot easier to understand. Let's say that we are designing our own numeric type. So we're going to design our own numeric type, for example, a rational number. And we want this numeric type that we're designing to be able to benefit from generic machinery. For example, a generic function that sums all numbers inside a list. If we have a generic function that sums all numbers inside a list, we would certainly want it to be able to sum all the numbers of our custom data type. We would want it to be able to do that. The object-oriented way to do that is to create an interface, much like this number-like thing, that says, okay, for any data type that can support the operation of addition, you simply extend number-like in your data type, and you implement the plus method. And that gives us an interface on top of our numeric data type, and we can code to that interface, so we can write generic code that can work with all data types that extend that interface. So when we go along to build our custom data type here called rational, we simply extend the number-like interface and we implement the plus method. This is a means of abstracting over different data types. It's recognition that many different types of data will support that plus operation, and we want to write generic code that can work with all these different data types. Once we have something like that, we can now define a generic sum-all function. And this sum-all function says, hey, I can sum values of any type A so long as A is a subtype of number-like of A. With this generic function, we can now sum up a bunch of rationals. But of course, we can use sum-all to sum not just rationals, but lots of other things too, so long as they extend number-like. And therein lies the problem. Because there are lots of data types out there that you can add that don't extend number-like. For example, all the standard ones built into Java, from byte all the way up to double. Not just those, by the way, but other data types and things like Spire and Algebraic and Spark, all these different libraries out there, they don't extend number-like. Not only do they not extend number-like, but also we can't make them. they're third-party data types. We don't have any control over their inheritance hierarchy, so we can't make them extend one of our interfaces. And that's the number one drawback to programming, to abstracting using the object-oriented style of creating interfaces that are extended by the data types that support the operations. The fix to this, however, is really quite simple. And it involves taking that interface and pulling it out of the data type. So you're still going to have an interface. It's still going to support the operation of addition, but it's going to exist outside of the data types. You're pulling the interface out of the object and making it stand alone. And when you do this, and you add a few other things to it, it's called a type class. A type class allows you to see similarities, utilize similarities between totally different data types. For example, use the similarity that many different types of data types can be added. Numeric here is now a type class that has a single operation that adds a left and a right together and gives us back another array. Now this is not extended by rational or any other type. It exists outside that. There's a moderate amount of boilerplate that we have to add to model type classes in Scala 2.x, but the good news is it's all going away in Scala 3. So Scala 3 has direct support for type classes, and all the boilerplate that I'm about to introduce just magically disappears in the next version of Scala. This thing here is called a summoner, and this allows you to obtain an implementation of the numeric type class for a given type, so long as it's been provided into implicit scope. And this thing here, called the syntax class, basically adds methods to all values that have an implementation of this type class for the given type. The net of it is this syntax class allows you to use object-oriented syntax, that is, use plus as if it were a method on any value for which there exists an implementation of the type class. So look up this pattern if you're interested in learning more about it. It's not super easy to encode into Scala, but once you learn the pattern, it becomes secondhand nature, and then you can rest at ease in the fact that the boilerplate will go away at some later date when everyone's using Scala 3. Once you have one of these type classes, you create an implementation of this type class for every different data type that can support those operations. And you make that implementation implicit so Scala can find it when it goes to look for it. In this case, we can create an implementation of numeric for the rational data type that we came up with, and we just make it implicit, and now Scala will find that when it's looking for things that support, for example, the plus method. Using this technique and another feature of Scala called a context bound, we're able to write the exact same sum all that we did before. Instead of saying A is a subtype of number like of A, we just say A must implement the numeric type class. And then we can implement it exactly as the preceding definition, thanks to the syntax class. So this doesn't change a whole lot. It's almost the exact same. And if there were no other differences between creating interfaces and mixing them into our data types and type classes, then of course we would definitely prefer interfaces, because we've got more boilerplate to create, at least right now in current version of Scala, to use type classes. But this is not the only difference. The big thing here is that, in addition, of course, to summing up all rationals, we can create implementations of this type class for third-party data types. So all the data types built into Scala, we can create implementations of this type class for them. And not just the ones built into Scala, but third-party ones in Spire and Algebra and Spark and so forth, we can make it all. So in other words, type classes give you the ability to abstract over not just your own data types, which is what object-oriented design patterns give you, but over all data types, even the ones you don't control. They are strictly more powerful, more expressive way to solve the exact same problem that interfaces solve in the object-oriented world. And not only that, but there are some cases where you actually can't solve the problem with interfaces. An example would be, let's say you're writing a serializable interface. Then the serialize is very straightforward. The serialize method is very straightforward. It just returns like JSON or whatever you're serializing to. But the deserializing one, what are you going to do about the deserializer? You don't call that on an object because the object doesn't exist yet. You call it on JSON and you get back a deserialized object. So this is a frequent source of trouble in Java land and has led to some weird anti-patterns, like, for example, Java's serialization having these read object and write object things that you create a bogus thing and then you overwrite its mutable fields with valid data when you deserialize it. These are very common anti-patterns in Java that arise from the fact that the OO style way of doing abstraction does not work particularly well. And with type classes, of course, you don't have that problem. There is no object to worry about. So you can have a deserialize operation on a standalone type class that takes JSON and gives you back a value of the deserialized type. And that works just fine. Not only that, but type classes have this really cool capability to participate in automatic derivation. What that means is we can write an implementation of this numeric type class for a tuple, assuming we have an implementation of the numeric type class for whatever's on the left-hand side and the right-hand side. And now, auto-magically, this truly is really amazing to see, we can start summing up not just tuples of things which are numeric, but tuples of tuples of tuples of tuples of things that are numeric, and so forth. And if you do this for lists and all the other data types, then you can compose all these data types together, and Scala will figure out how to add them up using the numeric type class, because we've given the derivation for all the recursive data types, and we have the base case, so it can derive the numeric instance for compositions of all those different types. And that's an amazing and very, very powerful capability that people utilize to great effect in the functional side of Scala. Finally, my last tip is going to revolve around basically code that looks like this. So there's a lot of code that looks like this in object-oriented code bases, Java code bases, and so forth. And it's really hard to understand a lot of object-oriented code precisely because you've got all these overrides. You've got the ability to override functionality that was defined in a parent class or parent trait. So all the subclasses, subtraits, they can override anything defined in a parent. And so you've got this weird situation where to understand this function here, initialized, you need to go up and understand the definition in the parent. And not just that, by the way, but the parent may call things that are only defined in the child. And those things defined in the child may call things defined in the parent. It's worse than that too, because what if you have one class and you extend it by another and another? You can get into crazy situations where methods are calling stuff defined in siblings, and those are calling stuff defined in parents, which are calling stuff defined in children, and so forth. It's very hard to understand this tangled mess. In fact, tangling is associated with object-oriented programming. That word, spaghetti ball, in fact, have you ever heard that? Like spaghetti ball of a code base. These come from object-oriented design principles. And I'm not saying that this is considered good in OOP land. It's not. In OOP, they say, hey, stop inheriting and start composing. They say favor composition over inheritance. That's an OOP best practice. And it's important to understand that these massive tangles result in difficult to understand code, because what they do is they take the implementation for something that should be local. Like ideally, you would have a function and you would be able to look at its body and understand what it does locally. But what object-oriented design techniques do is they take that implementation and they scatter it across an inheritance hierarchy. Inheritance hierarchies are graphs. And so now to understand the behavior of this method, you suddenly need to go and poke at an unknown number of classes all of which have their own mutable states and their own overrides and their own parent classes and their own subclasses and so forth. You need to put all that inside your head. And if it sounds difficult or impossible, it's because it is difficult or impossible. In big code bases, you can't understand what's going on. You can draw the graph of the object-oriented inheritance hierarchy, but it's just a tangled ball. It looks way worse than this, actually. And it's impossible to understand what's really going on in any given method. And even though the tip I'm going to give you is not going to solve all your problems, it's going to help. And that tip is very simple, and it's not going to go all the way. So going all the way would be saying we are always going to compose and we are never going to inherit, which you can do, but that's too big a step. For most teams, most code bases, that's too big a step. Instead, I'll just recommend that you either make methods final or you make them abstract. So either a method is totally abstract, it defines some sort of critical logic that will be implemented by a subclass or a subtrait, or it is final and cannot be overridden, in which case it could be considered a definition. This is a definition of what this function is in terms of the other ones. And this is a very simple rule to police in pull requests. Every method is either final or abstract. You can review that locally. And so you can prevent people from, if you get your team on board with this idea, you can prevent them from doing anything else quite simply, because this can be determined by inspecting a given line of code. And what that does is it helps cut down on the number of tangles in your code base. It prevents certain types of tangles from arising. And it makes it, even though it doesn't entirely eliminate the problem, it does radically simplify the ways in which you can utilize that object-oriented hierarchy. So I consider it a nice middle-of-the-road approach that gets you a lot of the benefits of doing full composition and no inheritance, but also it retains some familiarity and comfort level for object-oriented programmers. Many of us came from an object-oriented background, and we know how to do things in that world. And so you can still do stuff in that world, but with a little bit of a handicap that actually will improve the quality of your code base over time. It looks like I have one more in this section, and that is revolving around the use of type bounds. It's very tempting when you start using generics to use type bounds, that is the less than and colon operator, or the other one, the super type bound, to encode relationships between different parts of an OO data hierarchy. This is a natural instinct that all of us have if we like type safety. If we like type safety, then what we do is, instead of making something fully generic, we use a type bound to try to lock it down. And in my experience, looking at a lot of code that uses type bounds to try to improve type safety, I don't think it works that well. I think it works very poorly. I think what ends up happening in many cases is, here's an example of where we're able to say, we're modeling a product, and every product has some type of ID, but different products are potentially going to have different ID types. So for example, a movie will have a movie ID. And this seems like a good idea, because then what we're able to do is we're able to say things like, oh, well, my movie extends product of movie ID, and therefore we know for a fact that when we access ID inside a product, it is a product ID, so we have whatever structure is given to us by product ID, which might not be a lot, but it's some structure. Anytime you access a product and you don't know what that type T is, you still have a compile time proof that T is a subtype of product ID. So if product ID has methods or fields or stuff, you can access that always from your code base, which seems like a good idea. The problem is these subtype bounds create tangled relationships in your object-oriented hierarchy, and the more you extend these classes with other classes, then the more tangles are created. And then you're going to be tempted to introduce methods to copy stuff, or methods that can operate generically on things like this. And if you try to create a method that can operate generically on all products with something like this, They're going to fail. And the reason is that subtype bound. This type is erased at runtime for a very good reason, actually. It's erased at runtime. So you can't make generic code that can just create new t's or copy t's around or do stuff like that. You don't have that capability. So what's going to happen is if you try to abstract over this, you create code that can work generically over all different types of products, then most likely you will end up in a situation where you know something to be true, but you can't prove it to the compiler, so you end up doing unsafe casts. So in the very act of trying to create a precise data model that uses subtyping to express the relationship between different parts of our object-oriented hierarchy, we end up creating something that we still have to cast anyway. And this happens all the time. Anytime I've seen subtype bounds in a code base trying to improve type safety, I also see casts because they weren't able to carry that through all the way. So what's the alternative to subtype bounds? Well, I would say stop tangling up things that are better left unspecified. Just omit information entirely. Make things fully generic to the extent that that's possible. Because here, we're at least acknowledging that we can't do anything with t unless we know what it is. We can't do anything with t. Before, this preceding example was saying, well, maybe we can do something. No, you can't do anything with t. You don't know what it is. All typing information, that type parameter will be erased. You shouldn't try to play those games. They're not worth it. So let's just erase all information and say we don't know anything about t. And this results in detangling. We can make copy methods. We can make a lot more useful generic code. And not only that, but it forces us to, if we do need some structure on t, it forces us to introduce something. It forces us to introduce a set of capabilities on t. And that set of capabilities could be described by a type class. So we can introduce a type class that gives us whatever we want to do with t. And if we actually honestly need to know, in this example, that every t is a product ID, then there's another way to do that that doesn't involve type bounds. And that is introducing what's called a prism, which comes from optics. And prisms allow us to state, basically as a runtime proof, that in this case, every t is a product ID. Every t is a product ID, or can be converted or can be viewed as a product ID. And this gives us the capability to do not just everything we would have been able to do in the preceding example where we have the subtype bound, but many other things. And also, it's less constraining than the subtype bound. The subtype bound says t has to extend product ID. This one doesn't say that. It just says we know how to get from a t to a product ID, which is way more liberating. So my recommendation is, because I've never seen any case where type bounds worked out well, all the examples I've seen, it ends poorly. My recommendation is only use the type bound thing when you have to because of declaration site variance. And don't use it otherwise. Instead, when you're trying to make good data models, just make things as generic as possible. Don't constrain your type parameters at all. And then if you need to constrain them in some method, use a type class. Or if you positively need to maintain some sort of relationship between types, then do that as a function or a prism or something that you store inside the data structure. And this results in way less tangles, and you don't need unsafe casts or other types of just weird things that I've seen in these code bases if you use this approach. Yeah, you absolutely don't need it for cases like this either. So you don't need it in your data modeling, and you don't need it for methods. Because any place where you're tempted to use a type bound in a method, you can always replace that by a type class. And any place where you're tempted to use a type bound for some data type, you're better off with full polymorphism, unconstrained polymorphism, and either selectively introducing functionality using a type class on methods that actually need it, or reflecting a relationship using a prism or a lens or some other data structure. Functions. Let's take a look at a few tips for writing better Scala functions. Number one is prefer values for expected errors. So when we expect that a function is going to fail, then we want to make sure that our application logic handles the failure case. Why? Because we expect it to fail. It's part of the ordinary operation of the function for it to fail. So we expect and want our application logic to be able to handle the failure case. When you rely on exceptions to propagate expected errors, then the compiler can't help your fellow teammates out to handle the failure modes, because the failure scenarios are not reflected in the types. In this case, we have a parseInt function, and the type of this says, give me a string and I'll give you back an int. Of course, that's not actually true because there are many strings you can give this parseInt, and you're not going to get back an int. You're not going to get back an int at all. You're not going to get back anything. It's actually going to blow up. It's going to throw an exception. And the fix to this is quite simple. If we expect that parsing a string to an int can fail, then we want our application logic to handle that failure mode, which means we want the Scala compiler to help the developer handle the failure mode, which means we want to reflect the failure mode inside the return value of that function. A very simple change here, just instead of using exceptions for normal control flow, just switch over to using return values. Give your functions a type that doesn't lie. If you say you're going to give this function a string and it's going to give you back an option of int, this is a promise you can keep. Not only can you keep this promise when you implement this function, but developers who look at the type signature of this can understand the promise that it's making, and the Scala compiler will force them to deal with the very real and expected scenario that the string they're trying to parse is not in fact an integer. There are different types of data structures in Scala and beyond Scala that we can use to model failure. And the type you choose depends on, or should depend, on how many failure modes there are. So if there's exactly one failure mode, and the example of parseInt is an example where there's just one failure mode, the only reason that you can fail to parse a string as an integer is if there was no integer in the string. That's one failure mode. So in that case, you can use option to reflect the fact that there's only one failure mode to a developer. Because now a developer sees option and they're like, well, it was either there or it wasn't. But there's no explanation for why it wasn't there because we don't need an explanation because there's only one way it can fail. Of course, not everything has just one failure mode. Some code can fail for any throwable. And there's a type in Scala that can model that. It's called try. Try models some sort of function return value that can fail for any throwable. It would be an error, however, to use try on parseInt. Because the developer looking at that will say, oh, I can parse an int, and who knows, there might be 1,000 different ways it can fail, all mapped to 1,000 different throwables. That's too big. That type is too big for parseInt. But it's a perfect fit for many other functions. Some functions can fail, have a failure mode, more than one failure mode, and that failure mode is not throwable, it's some other data type. It could be some sort of domain error, some ADT that you built, or maybe it's a string, who knows what it is, but it's not throwable. And to handle that, you can just use either. And then finally, some data types or some functions can fail for some arbitrary reason, but in some sort of effectful way. For example, maybe async way. You make a database call, or you make a call to Redis, or you pull some stuff back from Kafka. These are asynchronous, and they also have the possibility of failure. And that error type will differ depending on the application. And for that, you can use an even more powerful data type like the Zio effect or some other functional effect system that allows you to model the asynchronous, parallel, concurrent nature of the problem domain, as well as model the fact that it could fail for a specific known reason. Number 9, defer nondeterminism. At different points in our application, we're going to be tempted to do non-deterministic things inside our application logic. An example would be we're going to retry something later. These two slides are flipped. Ignore that. Minor typo. Okay, so let's start with this one. So let's say we're going to retry something later. And this one is calling math.random. And the problem with math.random, of course, is that the source of indeterminism is coming from a global variable that's stored somewhere way out there. And so when we go to write a test for a retry later, it's going to be quite difficult, because that source of nondeterminism is not an input to the function. So the way to solve problems like these, and another example would be some bit of code that does a calculation based on the current time. If it calls system.currentTime millis, that introduces a source of nondeterminism into that function. And nondeterminism is really nasty to test. Really nasty to test. And obviously you can do the whole pure FP thing, which will solve that problem. You don't even have to go all the way there. All you have to do is take that source of nondeterminism and pass it into the function. So you can pass in now into the function that does some sort of time calculation. You can pass in a random number generator into the function that needs random number generation facilities. And this doesn't solve the problem in a global sense. It just pushes the problem up higher. It says, okay, well, I need nondeterminism. In order for you to call my function, you're going to have to give me that nondeterminism. And in so doing, what you're doing is you're pulling that nondeterminism effect up higher in your application, making it possible to do better and easier testing on your application logic, which is always a good thing. So whenever you run into nondeterminism, always try to push that higher in your application. Someone has to call the random, someone has to call system time now. It doesn't have to be you right there. It can be done at a higher point, allowing you to test this code that you're working on right now, quite simply. And number 10, the most advanced technique that will lead you down to a functional effect system like ZIO, ultimately in the limit, or something else like ZIO, is instead of doing things like, for example, charging credit cards and sending emails and whatnot, instead of doing that inside your business logic, instead create data structures that describe what you want to do. And the chief advantage of this approach is that you can express your business logic in a way that can be tested without having to do any mocking of external components. So when your business logic merely builds a description of something to be done at a later date, then you no longer need to involve any mock credit card processors or mock email servers or mock REST API. You don't need to involve that in order to test the business logic. And you can push that up higher. And this is, of course, a more advanced form of this technique is behind functional effect systems like ZIO. All right, I'll cover two tips for types. The first one involves the use of implicits. So implicit types are quite powerful, almost too powerful. And that's why in Scala 3 they're sort of being deprecated in favor of type classes, basically type classes and extension methods. So those two things are being built into Scala 3. And we don't, instead of having this low-level machinery of implicits, which could be used to solve a lot of problems and also solve a lot of non-problems, and also confuse a lot of developers and confuse IntelliJ IDEA, instead of having that, we're going to have two very special purpose features that take the best, like the winning applications of implicits, and make it easy to use them. Extension methods, and then type classes. Very, very powerful, very specific features that we know how to use, we know what they're good for, and they're hard to misuse. But for now, we have implicits, and implicits, they have the following drawback. When you call methods like sumAll, they require an implicit. If you call methods like futures flatmap and so forth, then they also require an implicit execution context. And Scala finds that implicit value by looking inside the lexical scope of the function that you're calling. So it's going to look outwards in the current code block, and then it's going to look up and so forth, and it'll look in the imports and whatnot. And what that means is the actual implicit that it finds is going to depend on exactly where that line of code is. If you move that line of code down 2 code blocks, Scala might find a different implicit. If you copied that line of code to a different file, Scala might find a different implicit. But what that means is that the meaning of your code, that is its runtime behavior, when you're using implicits, depends on lexical scoping. You copy-paste code from one file to another, or even move it down a few functions, and suddenly you might change the meaning of your program. It'll still compile. Scala still found the implicit, but it might be finding a different one that has totally different meaning. And this leads to lots of bugs. In fact, I've seen lots of bugs with Future in particular, because different scopes will have different implicit execution contexts, and you run the wrong computation on the wrong pool, and many times it will still work. For a while, eventually it won't work, and figuring out what went wrong takes a lot of time and effort. How do you solve this problem? There's one simple rule that you can follow, and it's called global coherency. Global coherency means for any given type, you're going to have at most one implicit that Scala can find for that type. Now, you cannot do this with execution context, unfortunately. That's because this is the design of Future. It's a reason to not use Future and use something else. But you can do it for your own use of implicits. So if you have things like number-like or numeric, in our type class example, you have numeric, you can avoid creating more than one numeric for a given concrete data type like rational. And not only can you avoid creating more than one implicit for a given type, but you can choose to put that implicit in either the companion object of the type class or the companion object of the data type to help Scala find it and to help make sure people don't have to import any implicits in order to use some bit of functionality. Importing implicits is almost always a design smell. You shouldn't have to import implicits. And if you have to import implicits, it probably means something fishy is going on, and you need to really seriously consider whether or not that's a good approach. And sometimes we can't avoid it. Like if you're using Future, you can't avoid it in many cases, but you can often avoid it. I mean, you always should. Number 12, and the final one, I really like this one. It's preferring one type per scope. And this is one of the ones that it's kind of hard to do all the way, but it's easy to do some of the way. And the more you do it, the more beneficial it is. An example of where this tip applies is, let's say we're calling the transfer data file function, and it accepts 4 Boolean flags. We have here 4 parameters, all of the same type. And what's wrong with that? You probably know what's wrong with that because it's bit you at some point in the past. You passed the wrong Boolean flag into the wrong position and something bad happened. This happens all the time. This is, in the case of Booleans, it's called Boolean blindness. But the problem is actually much bigger. The problem happens whenever you have more than one slot of a given type in a given scope. Ideally, you would have only a single slot of every given type in a given scope. And that way there would be no choice of where to put each value into the right slot. One way you can fix this transfer data file function is just create a bunch of case objects representing the on state, the true state, and then pass this function a set of these case objects. And then the meaning of this, of course, is quite obvious. Another case where this occurs is, let's say we're writing a function like transfer here, and we've got 2 different parameters of the same account type. What could go wrong here? Obviously, which one is from and which one is to, right? So in order to fix this problem, we just need to introduce 2 new types. We need to make sure that every parameter has a unique type. And so we could trivially create these wrappers, receiver and sender. So now when we call the transfer function, every parameter of our function has a unique type. And so now it's very clear what's going on. It's clear because of the names we've chosen. There are different types, different values, or rather different types in the parameters, so there's no possibility of confusing them. And we can pass around receivers and pass around senders and so forth. Maybe you even have a method that can convert a receiver to a sender, but that's explicit, and you can see that in the code base if someone does it. Another place where this happens is pattern matching on ADTs. It's very common in ADTs to have the same type at a higher level in the tree and also at a lower level. And so what happens in this example is when I call save settings, I've got the original settings at a higher level in the ADT. And then I've got another settings, which I called settings 2, at a deeper level in the ADT. And I've mistakenly passed the wrong settings to save settings. I wanted to pass the wrapped one, but instead I passed the original one. And bugs like this occur because they can occur. They can occur because we have two values of the same type in the same scope. And the goal, of course, is preferring one type per scope. So we don't want more than one value of a given type to appear in any scope. So this means in this particular case, we can use shadowing to make sure we can't refer to the outer settings. We can only refer to the inner settings. I actually, even though IntelliJ IDEA will warn like crazy if you do this, it will not leave you alone. But you can turn that setting off. And when you turn it off, you can always, always, always shadow everything that you possibly can. And the reason for that is you want to reduce the number of values in any given scope that have the same type to prevent yourself from making silly errors like the one I just made on the preceding slide. So these are the starting techniques that lead you down the path of functional Scala. And in functional Scala, we use a smaller part of Scala than the full Scala. And it's not that we ignore features that Scala has, at least not when we're doing it well. When we're doing it well, we use all of Scala's features, including subtyping. But what we do is we focus on the part that's easier to reason about and the part that's easier to test. And the part that ideally we can also explain to our colleagues in a reasonable amount of time. And that's functional Scala. So if you're interested in learning more about functional Scala, there's obviously lots of great material out there. And there's a library I work on called Zio that lets you do functional Scala, not just in the little parts that we've seen today. Like these are little chains you can make to your code base. You don't have to change a lot to start implementing these tips. And probably you're not going to get pushback from your teammates on most of them. They'll push back if you try to use fold instead of pattern matching. I guarantee you on that one. But a lot of the other ones, they're not going to push back. They're going to be like, yeah, this makes sense. Let's go ahead and do that. And then if you want to start exploring how you can build your whole application in a functional style, then you need a library that allows you to take side effects, interactions with the external world, like databases and caches and logs and all that stuff, and model that as pure values. And doing that gives you tremendous power as a programmer. You can start to solve problems that would have been extremely difficult or impossible to solve before, but does require you learn a slightly different way of thinking about it. Anyway, if you're interested in more doing FP in the large, so to speak, then please check out the Zio website. It's at zio.dev. And then actually that Gitter chat room has been deprecated. We moved to Discord, along with a lot of other open source projects. It seems Gitter's not so popular these days. So thank you very much for coming to this talk again. And thanks to Scala Hamburg and Felix, both Felixes, and Weem, thank you again. Really appreciate being here. And I guess I will be around eating that delicious cakes and muffins and stuff out there. So happy to chat with anyone after the fact. Thank you very much.
Yeah, take a pause.